Hello, my name is Stephen Price, and I am Team ME67. My project is implementation of filtered Rayleigh scattering with coupled particle image velocimetry for combustion applications. My sponsor is the Combustion and Gas Dynamics Laboratory here at the University of Connecticut, and my faculty advisor is Dr. Baki Sadajan. Measurements to analyze the detailed structure of a flame are quite complex. In order to achieve a better understanding, several laser diagnostics have been developed to determine flow field properties such as temperature and velocity. A laser sheet is directed through the flow, and a scattering signal is detected with an intensified camera. Light scattering is when light is absorbed by particles and then subsequently re-emitted at a different wavelength. Two common techniques used are laser Rayleigh scattering, or LRS, and particle image velocimetry, or PIV. As seen in the equations below, the detected laser Rayleigh scattering intensity measured can be related to the molecular number density, or N. Utilizing the ideal gas law and a constant thermodynamic pressure flow, temperature can be determined. PIV maps the two-dimensional velocity field in a flow by seeding with small tracer particles, illuminating them with a laser, and tracking their displacement over time. The scattering due to these tracer particles is called me-scattering. The effective me-scattering cross-sections are 10 to 20 orders of magnitude higher than that of Rayleigh scattering. This high-intensity me-scattering pollutes the flow field, thus inhibiting any possibility of capturing Rayleigh signal. Therefore, simultaneous LRS and PIV measurements are not currently possible in the lab. Due to varying translational velocity of the gas molecules, the Rayleigh scattering exhibits a Doppler shift from the incident light frequency, which can be seen in the graph. Meanwhile, me-scattering is caused by particles with a diameter equal to the wavelength of incident light and emits energy at that same wavelength. Therefore, by employing the use of a spectral filter, the Rayleigh and me-scattering signals can be separated for simultaneous detection. A modification of LRS is implemented in this project, called filtered Rayleigh scattering, or FRS, where the me-scattered light is absorbed by an iodine vapor cell filter. The transmission profile of iodine varies with temperature and can be adjusted until an optimal profile is reached. Using a DC power supply, the laser frequency can be tuned to coincide with an absorption band of the transmission profile. Sufficient absorption of me-scattering from particles in the flow is then achieved while permitting the passage of sufficient Rayleigh scattering for temperature calculation. Our approach was to optimize the filtration of me-scattering first by applying the FRS technique to a non-reacting CO2 flow seeded with water droplets, and then transitioning to a pre-mixed laminar Bunsen flame with particle seeding. Combined measurements of velocity and temperature via PIV and FRS were to be conducted for a number of different flame conditions. For example, flow velocity, particle seeding density, and mixture equivalence ratio. The deliverables of this project were a documented procedure for FRS along with a detailed error analysis. Figure 3 on the left shows the design configuration for imaging the non-reacting CO2 flow. An ND-YAG laser with a frequency of 532.06 nanometers was used. The laser beam was directed with optical mirrors into a series of borosilicate cylindrical lenses with appropriate focal lengths, shaping the beam into a thin sheet with a height of 2 centimeters. An intensified camera was aligned perpendicularly to the laser sheet for optimal scattering detection, along with a 10-inch iodine vapor cell that would operate at a determined pressure and temperature of 0.696 torr and 35 degrees Celsius respectively. An external DC power supply was purchased to finely tune the incident laser light frequency. To reduce undesirable background scatter and for safety during testing, laser sheeting surrounds the test section. To achieve a laminar CO2 flow with adequate seeding, a mass flow system was designed and constructed. As shown in the schematic, pressurized CO2 is directed through a regulator to a pressure gauge, where the flow is then throttled by an orifice and the nebulizer is used to form water droplets. Assuming atmospheric conditions, density and viscosity of CO2 were taken as 1.808 kilograms per meters cubed and 1.49 times 10 to the negative fifth kilograms per meters per second respectively. A conservative limiting Reynolds number of 2000 was chosen to ensure laminar flow. This results in a maximum velocity of 1.75 meters per second. Using a wet gas meter and a timer to measure volumetric flow rate at varying pressure readings, outlet velocity was determined by dividing by the cross-sectional area of the outlet. Because of the linear relationship between back pressure and outlet velocity, a line of best fit was calculated with the recorded values with a repeatability error of approximately 1 to 2%. Due to some unforeseen setbacks such as the laser being out of commission and COVID-19 pandemic, the deliverables were unable to be completed by the end of this academic year. However, as this is an accelerated master's project, progress will continue. Once access to the lab is restored, the first step is to achieve repeatable laser frequency tuning for optimal filtration using a high-resolution oscilloscope. Currently, during this hiatus, an image processing pseudocode has been written awaiting Rayleigh images for the scripts to be coded. Additionally, the design for a particle seeder to be used for PIV for the Bunsen flame is being finalized. Work will continue through the summer until a verified FRS procedure with a comprehensive air analysis is completed. Thank you.